Hello, I'm Dr. Sheldon Cooper, and welcome to the premiere episode of Sheldon Cooper Presents Fun with
Resolvers. Welcome to Life with David. I'm David. Today I've got a bunch of resolvers. I rediscovered these in my junk box recently, and I want to know more about them. So why don't you join me as we learn about what resolvers are and how they work. I'd like to spend a moment on safety. There's nothing more important than keeping you and your loved ones safe. Be sure to read, understand, and follow the safety rules for your tools. Using your tools properly will greatly reduce the risk of personal injury, and always use the appropriate eye, hearing, and respiratory personal protective equipment. Now let's get started! I got these 7 surplus resolvers about 30 years ago, and they've been languishing in my junk box ever since. They're used, and some of them need some attention to work properly. Since we're all locked down, I figured now was a perfect time to see if we can make them work. So what is a resolver? It's a rotary electrical transformer that's used to measure angular rotation, often to provide position feedback for servos and motors. Since resolvers have no electronics at the measuring device, they're very rugged and reliable. Resolvers are a very old technology. They were used during World War II for position feedback for weapon systems on ships and aircraft. How does a resolver work? Although there are several variations, operation is dependent on a rotor coil turning within 2 stator coils. The rotor coil is excited with an alternating current, which in turn induces a current in the 2 stator coils. Since the stator coils are at right angles to each other, the magnitude of the induced current in one coil is proportional to the sine of the rotation angle, while the other is proportional to the cosine of the angle. Resolvers use a change in phase to determine the quadrant of the measured angle. When the angle is between 0 and 90 degrees, both the sine and cosine coils are in phase with the rotor coil exciting signal. When the angle is between 90 and 180 degrees, the sine coil is in phase with the exciting signal, and the cosine coil is out of phase. Between 180 and 270 degrees, both the sine and cosine coils are out of phase with the exciting signal. Finally, between 270 degrees and 360 degrees, the cosine coil is in phase, but the sine coil is out of phase with the exciting signal. Back to my resolvers. I tested all 7 resolvers, and it looks like the rotor coils on most of them show open circuit. However, if I tap and turn the rotor, sometimes I get a reading. Let's take this one apart to see if we can find the problem. These resolvers have slip rings to energize the rotor coil. The slip ring can get dirty, which causes intermittent operation. To avoid this problem, brushless resolvers have been developed that use an additional coil to induce a current in the rotor coil. Let's try cleaning the slip ring to see if we can stop the intermittent open circuit. There are 2 clothespin shaped wires that ride in the grooves of the slip ring. It looks like the ring is a little tarnished. I'll use a little contact cleaner and some tissue to polish up the contacts. That looks better. The rotor coil now has a steady resistance of about 740 ohms. Let's clean up a couple more and see if we can make them work. These resolvers are designed to be energized with a 400 Hz signal. This is the frequency common in military ships and aircraft. so I'll use my frequency generator set to 400 Hz to energize these resolvers. However, the voltage will be much lower than specified. That means that noise will be greater in the output of the resolver, but that won't be a problem for what I'm doing today. First, we'll put the energizing signal on channel 1 of my oscilloscope and a stator coil on channel 2. It looks like we see the output vary as we turn the rotor. So far, so good. Now I'll try the other stator coil. That looks good also. Now let's see what the stator coil outputs look like together. I'll trigger the scope on the input signal and put the stator coils on channels 1 and 2. As you can see, as one stator coil nears maximum voltage, the other approaches 0. I also wanted to check out the phase differential between the signals. As one of the coils goes through 0 volts, the phase of the output signal shifts from being in phase with the exciting signal to being out of phase. A signal that's out of phase from the exciting signal can be considered the same as having a negative sign in front of the sine or cosine value. The wires on these resolvers are so thin that it makes it difficult to temporarily connect them together. I want to experiment a bit, so I mounted a couple of resolvers on some plexiglass, added a degree indicator, and a terminal strip to make it easy to swap connections. Let's compare the sine and cosine values we get from the resolver with the actual values. First, I tried putting both the sine and cosine on the same screen, but it quickly became clear that it would be too difficult to read the values. So I did one value at a time and adjusted the maximum value to be at full scale, that is, 40 divisions. Then I took the sine and cosine readings at 0, 30, 45, 60, and 90 degrees. I'll spare you the whole process, but here are the results. 0 degrees, sine and cosine. 30 degrees, sine and cosine. 45 degrees, sine and cosine. 60 degrees, sine and cosine. And 90 degrees, sine and cosine. Note the measured numbers were a little off from the actuals due to reading error, but not too bad for my makeshift degree indicator. Now I'd like to try using a couple resolvers for feedback control. What I'm envisioning is hooking the resolvers back to back and getting an error signal that represents the difference in position between one resolver and the other. After several different configurations, I found that by hooking the sine coils together and the cosine coils together and shifting the physical angle of the second resolver by 90 degrees, I could get an error signal that decreases to 0 when the position of both resolvers match. The error signal changes phase as it crosses 0, so the phase shift could be used to change the direction of a drive motor to drive the feedback resolver to the desired position. This results in a stable null position. However, there is an unstable null position when the resolvers are 180 degrees out of phase to each other. The reason this position is unstable is that any perturbation of either resolver will drive the resolvers toward the stable null position. There are several ways to avoid the unstable null position, including matching the drive speeds between the input and output, limiting the range of motion of the resolvers, or using dithering on either the input or the output. Dithering is when a slight motion is introduced to keep the output from being stuck in one position. I would also imagine that a more sophisticated circuit could be developed to avoid the unstable null position. That sounds like a good thing to try next time. Thanks for joining me today. We dug into some surplus resolvers that I had to find out what they're used for, if they work, and how they can be used to provide positional feedback. The next thing I'd like to do with these is to actually use them in a feedback application. If you like this video, please give it a thumbs up. If not, give it a thumbs down. And leave a comment or suggestion for things to do. I hope to do more of these videos, so please subscribe and click on the bell for notifications of new videos. Let's get together next time for another day in Life with David. See you soon!